Hey guys, welcome back to Unit 7, Lesson 1. Right now we're going to take a look at some examples of how to graph rational functions. So let's start off with our problem. Now remember, our first step in graphing is to factor your numerator and denominator. The numerator is just x, so that's fully factored. In our denominator, we have two terms. There are difference of squares, so we know it's going to factor to x plus 3 and x minus 3. Okay, so wholes. How do you find wholes? Remember, those come from your factors that are common to your numerator and denominator. You set them equal to 0 and you solve. Since there's no factors common to the numerator and denominator, there are no wholes. All right, so now vertical asymptotes. To get your vertical asymptotes, you take your factors that are unique to your denominator, set them equal to 0 and solve. We have two factors unique to our denominator, so we're going to have two vertical asymptotes. Whoops, I meant to put x minus 3 equals 0. All right, so I have x equals negative 3 and x equals 3. Now our x-intercepts, those happen when we cross the x-axis. When do we cross the x-axis? When y equals 0, so we set the whole function equal to 0, or the leftovers in your numerator. So in the numerator I have x, I set it equal to 0, so x equals 0. That means our x-intercept occurs at the origin. Okay, so for y-intercepts, what you have to do is plug in 0 for x and solve. So we have 0 over 0 plus 3 and 0 minus 3. Okay, so that's 0 on top is going to make it all 0. You'd have negative 9 in the bottom and you'd get 0. So again, our y-intercept is at the origin as well. Okay, horizontal asymptotes. We use our saying of bow, bought, and same. So the degree of the numerator is 1. The degree of your denominator is 2. So it is bigger on bottom. So that's an example of bow, which means we're going to have a horizontal asymptote at y equals 0. All right, and we're going to talk about our domain. We're not necessarily going to find it, but since we have 2 points of discontinuity, meaning we have 2 vertical asymptotes, no holes, that means we're going to have 2 breaks. So when we do our domain, we're going to have 2 unions and 3 sets of parentheses. Okay? All right, so now let's actually go through the process of graphing. So starting at the beginning, taking a look at our problem, let's factor it. So in our numerator, this is an easy factoring since our leading coefficient is 1. We know it's going to be x times x. Since it's a plus 4 and a plus 5x, we know it's got to be plus plus. Factors of 4 that add up to 5 are 4 and 1. Okay, and my denominator is already fully factored. It's x plus 2. So for our wholes, those come from the common factors. Do we have any common factors? No, so there are no wholes. All right, moving on to our vertical asymptotes. Those come from factors unique to the denominator. We only have 1, and that's x plus 2. So we set that equal to 0, and we solve for x, and we get x equals negative 2. So we're going to go ahead and graph that right now. So it's a vertical asymptote. We're just going to do a little red dotted line right there for our vertical asymptote. Okay. Now let's move on to our x-intercepts. Okay. To get our x-intercepts, that's when we cross the x-axis, the y equals 0. So set your factors in the numerator equal to 0 and solve. So we've got x plus 4 set it equal to 0, and we've got x plus 1 set it equal to 0. So x equals negative 4 and x equals negative 1, and we're going to plot those on our graph. So negative 4 is right here, and negative 1 is right there. All right, now moving on to our y-intercepts. So y-intercepts happen when we plug in 0 for x. So we're going to plug in 0 everywhere we see an x. So we'd have 0 plus 4 and 0 plus 1 and 0 plus 2. So 0 plus 4 is 4, 0 plus 1 is 1, 4 times 1 is 4, 0 plus 2 is 2, and 4 divided by 2 is 2. So we have a y-intercept at 0, 2. Okay. Now, moving on to our horizontal asymptotes, so that's bow, bought, and same. So if you take a look, your degree of your numerator is 2, your degree of your denominator is 1, so it's bigger on top. So that's bottom, which means there is no horizontal asymptote. So we have to check for a slant asymptote. To check for a slant asymptote, we are going to use long division. So take your numerator and put that under your division symbol. We're dividing by x plus 2. Remember with long division, you see, okay, how many times, what do I need to multiply x by to get to x squared? I need to multiply by x, and then we multiply. So we have x squared plus 2x, and now we subtract. So these cancel, we're left with 3x plus 4. We'd have to multiply x by 3, distribute. You get 3x plus 6, and now we subtract. These cancel, and I'm left with a remainder of negative 2. Okay, so my equation for my slant asymptote comes from right here. It's this x plus 3. So y equals x plus 3. So remember that means you cross the y-axis at 3, and you have a slope of 1. So I'm just going to kind of sketch that in by just putting dots on that slope of 1. Okay, so we have our slant asymptote. Now we're ready to graph our function. So as you can see, with rationals, you're going to end up with some curves, and they're going to kind of hug your asymptotes, but not really cross them. So if we wanted to talk about domain, because we have one vertical asymptote, that means we're going to have one union. 1 point of discontinuity. So we're going to start at negative infinity. We're going along until we get right to that vertical asymptote at negative 2, and then we pick up at negative 2 and go on to infinity. So let's try another example. So start with your factoring. So in our numerator, again, leading coefficients 1, make it easy on yourself. So it's going to be x and x. Because we have a minus 4 in the middle, that means our signs are going to be opposite, or minus 4 at the end. It's opposite signs. We want to get a positive 3. So we have to have a positive 4 and a minus 1. In our denominator, opposite. We want to get a positive 1 out, so it's got to be a positive 1 and a positive 2 and a negative 1. So now you can see we have a factor in common. That's what creates our wholes. So for our whole, we're going to set x minus 1 equal to 0 and solve for x. We get 1. So now we're going to take that 1 and we're going to plug it into our leftovers to find the y value. So we have 1 plus 4 over 1 plus 2. That's going to be 5/3. So our whole is at 1 comma 5/3. So let's graph that. 1 and 5/3 somewhere in there. Okay, now let's move on to our vertical asymptotes. So vertical asymptotes, remember you take the factors unique to the denominator. There's only one. It's x plus 2, set it equal to 0. You get x equals negative 2. So now we're going to graph that. Here's our vertical asymptote. And now we're moving on to our x and y intercepts. So our x-intercepts, remember you set your numerator equal to 0, or what's left in your numerator. So what we've got is an negative 4, so that is a point right there. Okay, now we're going to find our y-intercepts. So our y-intercept, okay, plug in 0 for your x's. So we've got, we can go back to our original if we want. We have 0 squared plus 3 times 0 minus 4, 0 squared plus 0 minus 2. All this stuff cancels, and negative 4 over negative 2 is positive 2. So we have a y-intercept at positive 2. Okay, and now we got to figure out our horizontal asymptotes. Notice that we have the same degree, so that means same simplify. 1 over 1 is 1, so we have a horizontal asymptote at y equals 1. So that's going to be right here. Okay, and we can kind of already see that curve for our top part, and we're just going to mimic that for our bottom left. And since we have 2 points of discontinuity, we're going to have 2 breaks in our graph. So we have negative infinity, 2, going along, and then we get that vertical asymptote, so negative 2. We pick up at negative 2, and we're going along, and we have that hole, and I really should have left that as an open circle instead of a dot. And that hole occurs when x is 1, and then we pick up when x is 1 and go on to positive infinity. All right, last example. Feel free to pause the video and try it on your own. So factor GCF of 3, you're left with x minus 4. Denominator, difference of squares, x plus 6, x minus 6. Because we have no common factors, that means we have no wholes. So let's move on to vertical asymptotes. So factors unique to the denominator set equal to 0. X plus 6 equals 0, x minus 6 equals 0. That means x equals negative 6 and x equals positive 6. So we're going to graph those. So, okay, and then here's our other one. Okay. All right, now moving on to our x-intercepts. So x-intercepts set the factors unique to the numerator equal to 0. Well, 3 can't equal 0, but if you set x minus 4 equal to 0, that gives you x equals 4. So we're going to plot that on our graph. Okay, and now let's talk about the y-intercepts. So y-intercepts, plug in 0 for x. In your numerator, that's going to get you negative 12. In your denominator, that's going to get you negative 36. And that simplifies to 1/3. So we cross the y-axis somewhere in there. Now on to our horizontal asymptotes. So bow, bow, bottom, same. You should notice your degree on top is 1, degree on the bottom is 2. So that's an example of bigger on bottom. That's bow, which means we have a horizontal asymptote right on our x-axis, which is kind of weird. All right, now this is not really enough information for us to graph our curve. So what we're going to want to do is we're going to want to plug in some other values for x. So I just chose randomly, like, because I want something to the left of that negative 6 asymptote, I plugged in negative 7. So if you find f of negative 7, you'll get out negative 33/13. Okay, so so go to negative 7 and negative 33/13, somewhere in here. So we have a curve down here. If we plug in positive 7, we get 9/13. So go over to positive 7, 9/13. So it's going to be somewhere up here. And then if you follow this curve, this kind of gives you the curve of that, because it gives you the curve there. So domain, negative infinity to that vertical asymptote of negative 6, union, negative 6 to positive 6, union 6 to infinity. And that's how you graph rationals.